Welcome to part 6 of the series of data fitting, and in this part we look at model selection and evaluation. So how to choose the right model and how to evaluate your fit and the best practices to make sure you get the best data. Let's consolidate what we have learned so far. Here is a visual gallery of all our model shapes. So we have linear, which we said is a straight line. Quadratic will give you a parabola. Exponential, it will show you rapid growth or decay. Sigmoidal, it will have S curve shaped with limits. Gaussian is symmetric peak, or sinusoidal, which is represented by oscillating waves. When you plot your data, just match the shape to this pattern. This reference summarizes when to use each model. So if there is a constant rate of change, as we mentioned before, it should be linear. Is there one turning point? Then you use a quadratic. Is there a proportional growth or decay? Then in that case you use exponential. Do you have a diminishing returns? Then you have logarithmic. Is there a limited growth that you've noticed in your data? Then you should use sigmoidal. Did you notice a symmetric peak? Just go for Gaussian. And finally, if there is an oscillation in your data, then go for sinusoidal. So I suggest you keep this handy when deciding which model to try first. Now let's build a decision tree for model selection. Let's start with the most basic equation. So as we mentioned before, is your data a straight line? Then if it's yes, then you use a linear regression. And that is y equals mx plus c. That is will explain well your behavior, your data behavior. If not, then we need to look at how it curves. Does your curve have just one bend? One turning point? Does the data go up then down or down then up? Then that looks like a parabola, and in this case you use a quadratic. So basically y equals ax squared plus bx plus c. Does your data show rapid accelerating growth or decay? Does it take off like a rocket or drop off quickly? Then if you notice this, then this is exponential. And the equation is y equals a times e to the kx. Positive k for growth or negative if you have a decay. Does your data level off? Does it approach a maximum or a minimum that it can't exceed? Then that looks like sigmoidal or logistic. So the growth is constrained by resources or limits. Is there a symmetry in your data? So bell-shaped peak. Do the data rise to maximum then fall in a mirror image? If that's the case, then it's a Gaussian. And like we mentioned, that's often seen in chromatography peaks, and in thermal analysis in melting endotherms, and in natural distributions. If your data has multiple turning points, it goes up, then down, then up again, then you need higher order polynomials. And I suggest you look into cubic for 2 turning points. And maybe you need higher degrees for more complex pattern. But you need to be careful about the overfitting problem. Finally, is your data oscillating? Repeatedly going up and down in a wave pattern? And if you see that, then this is a sinusoidal. And the way you describe this is y equals a times sine of b x plus c plus d. If your data is curved but not exponential, then you would expect that this could be logarithmic or power model which fit your data, which often used for diminishing returns behavior or scaling relationship. And as mentioned before, if the data levels off, peaks, oscillates or repeats, the tree
guides you to appropriate alternative. So use this flowchart whenever you're not sure which mathematical model to apply. Start at the top and answer each question based on what your data actually look like. Remember, the decision tree gives you a starting point, not a final answer. After fitting your chosen model, you must still evaluate the fit using residuals, goodness of fit metrics, and scientific judgment. If the fit is poor, return to the tree and try the next most possible model.
R squared, the coefficient of determination, and this is most commonly used measure of fit quality. It tells you what fraction of the variation in your data is explained by your model. So R squared of 1 means perfect fit, and if it's 0 then means there is no fit at all. Higher value for R squared is generally better, but you need to be aware because sometimes you can increase the R squared by adding more parameters, but that doesn't mean your model is better. Let's compare these fits. Look at the data. You can see how well different models capture the pattern. But remember, R squared alone does not tell you if you've chosen the right model. So you need to actually look at your data and residuals. The wrong model can give completely wrong predictions, even when you get a decent R squared value. If you force a linear fit to a curved data, your prediction will be widely wrong. This is why model selection matters so much. So get the functional form right first, then worry about the parameters later on. Residuals are the differences between your data and your model's predictions. Residual equals observed minus predicted. Always plot residuals, very important for your analysis, because they should scatter randomly around 0 with no pattern. Good residuals show random scatter around 0, and that indicates you have a good fit. On the other hand, you may have bad residuals, and bad residuals means they will show pattern. So a curved pattern means you've chosen the wrong model type. A fan shape, for example, for your residuals means you need to do data transformation. And one problem is outliers, and those should be investigated because they are like unusual points in your data. So if you see patterns, your model is missing some additional information, or possibly you're actually working on the wrong model. Overfitting is when your model fits the noise, not just the signal that you have, which are genuine from your data. And this often happens when you use too many parameters. So for example, if your high degree polynomial can pass through every single point perfectly, and in this case R squared equals 1. But between points it wiggles crazily, so in that case the predictions are terrible. So more parameters in your model doesn't always mean it's better. So always remember to use the simplest model that will capture the true pattern of your data. Let's look at some fitting mistakes that can happen during when finding the right model for your data. The first problem or the first mistake is forcing a linear fit to a curved data, and this is quite common, and it's obviously it's a big problem with this kind of trying to fit a linear shape to the curved data. So it's wrong. The other thing can happen is ignoring outliers, so the points which are the odd points basically. So one point or one bad point can skew your entire fit. So it will have a big impact on your fitting. The other problem is overfitting. That means using polynomials with a higher degree. So for example, you use polynomial degree 6 while you maybe degree 2 is enough for you, so that is gonna cause problems. And finally, you can end up with what we need to avoid here, which is extrapolation. So if you extrapolate too far, your model, remember, your model is only valid within the range that you have measured. So that brings us for good data fitting practice. So always plot your data first. Let the data tell you what is the shape. Then follow this by starting with simple fitting, trilinear. Then after that, polynomial. Then go more complex model only if you think this is needed. Always check residuals. They should be random with no pattern, as mentioned previously. Always report uncertainty. So include confidence intervals on your parameters. And you should always be honest when you report your data. So if the fit is not good, so you should really report that. Parsimony means choosing the simplest model that adequately fits your data. So basically, simpler is better. So start with the simplest model that might work. Only add complexity if you really need to. Remember, more parameter does not equal to a better model. So the extra parameter should be justified by the science. So just not because you want to have a better fit.
Extrapolation, predicting beyond the range of your data, is a common source of error in data fitting. So a fitted model is only validated within the range where data exists. Predicting beyond that range is risky unless the model is supported by theory. And this is what we've seen early on in Arrhenius model and the Kissinger model. So interpolation, which means predicting between measured points, is usually safe. However, empirical extrapolation using polynomial, linear trends, or arbitrary exponential often fails outside the data range. And that means to avoid this, we should use theory-based extrapolation. So again, Arrhenius is a specific example because their physical basis justifies extrapolation. And this is all based on the assumption that mechanism for that we use it for the activation energy for degradation does not change. So the best practice is to extrapolate cautiously, state assumption and verify whenever possible.
You have many options for fitting software. So you could use Excel, which is easy and accessible, available, and it's very good for simple fits. It will provide trend lines and line functions with equations and R-squared values. Similar to Excel, there is Google Sheets, Python with different libraries like NumPy and Polyfit. It's quite powerful and it's free, open access. You can have R, also similar to Python, similar functions. You could have more like user-friendly GraphPad, Prism. Also, you get Origin, which can give professional plotting software. I personally use Python, and I highly suggest you try Python among those because it's going to be very useful, especially if you are interested in advanced applications of data fitting such as machine learning applications. So let's recap all our models. Linear for straight lines, polynomial for curves with turning points, exponentials for growth and decay, logarithmic and power for diminishing return and scaling, sigmoidal for S-curved with limits, Gaussian for symmetric peaks, sinusoidal for oscillations. Make sure you match the shape of your data to the model shape. Check your fit with R squared and residuals and always keep it simple. I hope you found this series on data fitting useful for you. As mentioned, always look at the shape of your data, then choose the right model to fit your data. Thank you.